we're going to review your Desmos activity and explore the graphs of derivatives. So we have a reminder here that the derivative is the slope of the tangent line to a function at a given value. So if we drag this point along our function, we can observe how that changes the slope of the tangent line for any given point. We're asked to predict where the slope is 0 and then where the derivative will be positive or negative. So let's start with where the slope is 0. As I was dragging this along, remember slope of 0, that happens when we have a horizontal line. So that appears to be right about here at -1. And then it happens again here at 3. Now between there, you'll notice that my red function is increasing from -infinity to -1. After that, it becomes a decreasing function, meaning that the tangent lines here have negative slope. And then once I get to x equals 3, my function is increasing again, and these tangent lines here in purple have a positive slope. So anywhere that those tangent lines have a positive slope will be a positive derivative. Anywhere my tangent lines have a negative slope will be a negative derivative. So I can use these observations to answer my first few questions here on my note page. The derivative was equal to 0 when the original function has x values of -1 and 3. The derivative should be positive anywhere the original function was increasing, which was the interval from -infinity to -1, as well as the interval from 3 to infinity. So we're using interval notation here to represent both these pieces on my graph. And we're discussing the corresponding x values that go along with those. Now our derivative will be negative anywhere the original function was decreasing, corresponding to tangent lines with a negative slope, and that was the x values from -1 to 3. Notice that these intervals are all broken up by the x values where our derivative was equal to 0. Back in the Desmos activity, we can use the slider to verify our prediction. So as we move that, we are taking a look at different x values, and the purple points represent the slopes of the tangent line for each of those x values. So for example, here it tells me b equals 1. That's the x value of 1 right here. And we saw that that tangent line had a slope of 0. So these purple points are plotting the outputs of the derivative, which is that slope of the tangent line. And as we continue on with that, now you can see we have negative outputs corresponding to those x values between -1 and 3. So all this here between -1 and 3 corresponded to the decreasing portion of our original function, and these all have negative outputs for my purple derivative plots. And continuing, now we have positive values corresponding again to another increasing section on my original function. Back on our note page, we can summarize this. Item 4 asks what is happening in the solid red graph of our function when the dotted purple graph of our derivative is 0. So remember here, and that corresponded to those horizontal tangent lines. You could alternatively say that the tangent lines have a slope of 0 here, or anything similar to illustrate that point. And item 5 is the really important one here. This is one of the most This is one of the big concepts from this section. How does the derivative change when our function is increasing versus decreasing? So as we discussed in number 4, the horizontal tangent lines correspond to the derivative being equal to 0 for those a values or x values. The derivative changes here, increasing versus decreasing. We can say that our derivative is positive when our function is increasing. So that corresponded to, for example, here and here on our graph, or here our function was increasing and the derivative was positive as well. And we could say that our derivative is negative, so less than 0, when the function we started with is decreasing. For example, here between -1 and 3, our original function was decreasing, and our derivative had outputs that were negative. We have another example here on the Desmos activity that works nicely for you to verify these properties, but I'm going to skip ahead to slide 7 because this one got a little interesting. So we want to see where the slope of the tangent line is 0. Drag the blue dots to where we think the derivative will be 0, corresponding to those tangent lines having slopes of 0. We're also asked to consider what is happening at these sharp corners or cusps on a graph. So a lot of students here will observe the pattern that anytime we go from decreasing to increasing, we might have a 0 there, or from increasing to decreasing, we could have a 0 here, and again decreasing to increasing, so perhaps we have a 0 here as well. So I often see students guess these, but as we move on to the verify page, and if we take away those points from the derivative and then slowly bring them back, we'll see along here we have decreasing our original function. Our derivative has negative values. That's to be expected. But as soon as we hit -4, where we change directions and go from decreasing to increasing, we jump. There's a jump discontinuity here on my derivative. And that is because the original function does not have a smooth transition from negative to positive. These tangent lines have slope values of -5, -4.2, -4.1, and so on, and then suddenly jump up to positive values on this other side. So if I was to draw tangent lines along the graph here, they would all have positive values. Unlike what happens here at -2, where I have a smooth transition, my tangent lines are allowed to flatten out, and I get that horizontal tangent line here with a slope of 0, illustrated by the outputs of my derivative here. That doesn't happen at these sharp points. So that's why here for this derivative, we have jump discontinuities at -4 and 0. So moving back, our original prediction was incorrect, and we only have a true 0 on our derivative here at -2. Now here I've taken the matching page and paired up each function correctly with its derivative, and we'll quickly take a look at these so that you can make sure you got the correct answers and understand why or why not these are the correct pairings. So for our first set over here, I think it's always a good idea to start, whether you're graphing these on your own or trying to match them like this, always start by looking for those zeros. So for my original red graph, I see my horizontal tangent lines here and here corresponding to places where I would have zeros for my derivative function. And then I notice that to the left of this first 0, my function is decreasing. Therefore, I know I'm negative on that interval. In between my zeros, I'm increasing on my original function, so I know my derivative is positive. And then after, my original function is decreasing again, so I know I'm negative on that interval. So that tells me if I go from negative to negative for my derivative, I should have a graph something like that. It's not perfect. If I wanted to be more exact, I could go in and actually sketch out some of the tangent lines and perhaps use a ruler or something to count what those slopes are, and then actually plot each of those points as we observed. Oh, I put that negative, it should be positive. Plot those points as we observed in the Desmos activity. But that would be a little hard on this particular function because we don't have a nice grid to actually compute what those slopes are. But we can at least see the 0 there, negative, positive, negative, and that matched up with this function down below. Moving a little quicker now through the next few, I can see this red parabola has a 0 corresponding to that horizontal tangent line, increasing before, decreasing afterwards, positive and then negative, matches up with that line right there. Similarly, for this parabola, I have a tangent line here with a slope of 0, so I should have a 0 somewhere to the left of the y-axis like we do in this line, decreasing and then increasing, so negative and then positive. Now this absolute value function is interesting because we have this sharp point right here, and as we saw, sharp points don't allow that smooth transition, so there actually isn't a tangent line with slope 0 there. That doesn't happen, which is why we have this jump discontinuity at that corresponding x value there. So we go from a constant slope here, so whatever that value is, maybe it's -1, -2, that is a line with a constant slope, which is why you see this portion of the derivative having just a constant value there. Similarly, on the right-hand side of our discontinuity, it's positive now though, but it's still a constant slope for those tangent lines. Therefore, we have a constant line graphed here. All right, now our last two here. This is a constant function. There is no change. Therefore, the derivative is 0, which you can see we just have the horizontal line here graphed at 0. And our very last one, it's also linear. So its rate of change, remember, it all comes back to the idea that a derivative is a rate of change. Rate of change here is just the slope. This has a negative slope. Therefore, its derivative is negative, and it's constant because the slope of this original function is unchanging. All right, just to wrap things up here, remember you can try out graphing directly on these Desmos activities. This is where I mentioned that we might be able to get a little bit more accurate points graphed on these rather than just that quick sketch, by actually taking a look at, if here at -4 I wanted to sketch that tangent line and say, all right, let me try counting the slope. If I go down 1, 2, 3 over 1, maybe this has a slope of -3. Therefore, at -4, I should put a point at -3. And then I could repeat that process for -4 here, graph that tangent line, compute its slope. It looks like maybe -2, put a point there, and so on to help me calculate that a little bit better. But as long as you're getting the shape, I'm happy. That's mostly what I'll be looking for, is can you make those connections between increasing and decreasing on the original function with positive, negative values of the derivative. That's really the most important thing here. And then as well, if we move on to the very last slide, hopefully you saw that you can make the original function and its derivatives appear and check your answers to see if you were correct or not. And you guys can decide how accurate I was on my sketch that I just showed you. And you can check your answers for the other two functions as well, clicking on these circles to make those appear and disappear. And we have another discontinuous derivative here as well because of the sharp points in the original function.